Hi everyone, I'm Kenzie Nimmo. I'm currently an Einstein Fellow at Northwestern University. I'd like to thank the organizers for putting together this meeting and inviting me to give this talk. I'm sad, like Vic, that I couldn't be there in person, but yeah, hopefully you still take something away from my talk and maybe we can have some conversations over Slack. Maybe in the morning though, it is 11 p.m. here. Okay, so I'm going to give an overview of FRB emission physics more from an observational point of view. I'll start with showing that the FRBs show a huge diversity in their burst properties. So they show a range of spectral properties, temporal structures, polarization properties, and I've tried to encapsulate that diversity here. The question in my mind is, does this diversity, is this a reflection of different progenitors, different emission physics, different immediate environments that introduce propagation effects on the signal? I think likely it's probably a complicated mess of all of these things. And so it's important that we can try and disentangle this to understand about or get a complete picture of the underlying astrophysics of the FRB population. So to try and focus on the emission physics, let's go through what properties are kind of broadly true for FRBs in general. So here I'm showing the transient phase space plot, which is luminosity on the y-axis, transient duration on the x-axis. The FRBs are in blue, and I'm comparing here to kind of galactic sources, so pulsars, rotating radio transients, SGR 1935, for example. And from this, we can see that FRBs are coherent. They have very high brightness temperatures that you can see as these diagonal lines. They're short duration, typically around a millisecond. They're luminous. They emit exclusively in the radio, excluding the galactic magnetar example. So far, we've seen them down to about 110 megahertz and up to about 8 gigahertz, as far as I remember. And they're also highly polarized. So here I'm showing some bursts from the first repeating FRB, 121102. And you can see in these four bursts that the red line matches the black line. The black line is Stokes' I, and the red line is linear polarization. So they're 100% linearly polarized. So from these broad properties, the two kind of classes of emission models arises. Of course, there's many models in the literature proposed to explain FRB emission, but they can kind of broadly be grouped under these two categories. And for the purposes of this talk, I'm going to keep it high level and just talk about these broad categories. So either the emission is coming from within the magnetosphere, maybe there's magnetic reconnection or bunches of electrons that are being accelerated along magnetic field lines. And that's the magnetospheric models. And then the non-magnetospheric models, you have a central engine that releases energy in the form of a shock. That shock propagates far out from the central engine and produces the FRB at far distances. So to test these models, I'm going to focus on these 5 observables that I'm showing here. So spectral behavior, the temporal variability, polarization angle behavior, circular polarization, and scintillation. Let's just work through these one by one. So starting with spectral behavior, FRBs can be broadband or narrowband, as I'm showing here. Kind of up until recently, broadband was kind of at the whim of the telescope that you're using, exactly how wide your bandwidth is. But we have recently detected some FRBs, co-detected some FRBs with CHIME and DSA. This is work in prep by Jacob Faber at Caltech. And that's really cool because it tells you that this FRB at least spans from 400 megahertz at CHIME all the way up to kind of 1.5 gigahertz at the DSA. Also on spectral behavior, some repeating FRBs show this downward drifting frequency structure or the so-called sad trombone effect. Yeah, so this is basically that the frequency structure drifts down the frequency structure drifts down as a function of time. Rarely we've seen it go up. Most of the time it goes down. Unfortunately, this variety of spectral structure can't really distinguish between these models. In this Metzger et al. 2022 paper that I cite here, they introduce a toy model where all it requires, it doesn't matter what the underlying emission mechanism is, all it requires is that you have a narrowly peaked SED with a peak luminosity and frequency that scales as power laws from a singular point in time. And that could be like when the central engine releases energy, for example. So in the case of magnetospheric models, you can have radius to frequency mapping in the emission, like as the emission region moves out as a function of time in the magnetosphere to create this downward drifting structure. And for the shock models, you could introduce that the shock is decelerating as a function of time, and that would produce the same kind of morphology. This toy model also explains not only the drifting structure that we see here, but also this kind of like blobby structure, where all that's tweaked between these things is the power law index of the drifting, which we don't know. And so it's possible that different sources could have a different index on that power law. The one thing that this toy model can't explain is the fact that non-repeaters tend to be more broadband and the repeaters tend to be more narrowband. And so that indicates that at least this drifting power law has to be, under this toy model, has to be different between repeaters and non-repeaters. And so it remains open how to explain that difference. Maybe it's different progenitors or physical processes, or there's maybe a difference in their environments. Okay, but what about temporal properties? Well, we see a huge range of timescales in FRBs from sub-microsecond all the way through to seconds. And for the shortest timescales, the 60 nanoseconds here, if you assume that just a light travel time argument, then you get an emission size of about 20 meters. So that's really tiny. And inside a magnetosphere of a compact object, you're going to expect that the emission region must be very small. And so this is completely okay in the magnetospheric model. But of course, here we've excluded any relativistic effects. And so if you take into consideration relativistic effects, you get this equation, which relates the variability time delta t with the emission region, R emission, and you have on the bottom this gamma squared, which is the Lorentz factor. So you can basically just boost the Lorentz factor, and that lets you boost the size of the emission region. And so unfortunately, the emission region size might not be as tiny as you would think from a light travel time argument. But for the non-magnetospheric models, there is a similar relation between the total width of the burst, the emission region size, and with the same dependence on the Lorentz factor. And so by combining these two equations for these non-magnetospheric models, it requires that the total width has to be comparable in scale as the variability time. And that's not true observationally. In the FRB that I'm showing here, we see kind of 3 orders of magnitude difference in the variability time to the total width. And we've seen that in other FRB examples as well. So not naturally explained in the non-magnetospheric models. However, I will add a caveat to that statement, which is that there is growing efforts going into studying nonlinear propagation effects in these extreme environments. And in both of these, so Bhaswati et al. 2021 and 2024 papers, they discuss that these propagation effects can introduce this sub-microsecond variability. And so while it's not naturally explained by these non-magnetospheric models, you can potentially introduce a propagation effect to explain this temporal structure. So I've added a question mark here to indicate the hesitancy. Okay, so polarization. Here I'm showing a kind of summary plot from the first CHIME baseband catalog's polarization results. In the top panel here, you can see that we have 50 out of 88 in our sample that exhibit flat polarization angles across the single component. And then in the third panel here, you can see that there's 19 out of 88 that exhibit flat polarization angles across multiple components. And so that's telling us that most commonly these FRBs have flat polarization angles, and that implies that they have highly structured magnetic field configurations that aren't changing rapidly. But sometimes we see jumps in the polarization angle, very sharp and fast changing polarization angle behavior, as shown in this plot here, but there's many other studies in the literature that shows this kind of behavior. And so that's implying that you have this sudden and abrupt change in the magnetic field configuration. This could be explained as seen in pulsars, so it can be explained in a magnetospheric process. So you can imagine things like magnetic reconnection, where the magnetic field is reconfiguring, and that could create this sharp change very quickly. For the non-magnetospheric models, it's possible that you could also have magnetic reconnection. I believe that, at least from my understanding in these shock models, polarization hasn't really been well studied. So that would need to be explored further. But I think conceptually you could think that magnetic reconnection could happen in these shock models and also explain these kind of sharp jumps in the polarization angle. But recently in CHIME, we found an FRB that exhibits a really smooth S-shaped polarization angle swing, as you can see here. So this smooth polarization angle behavior is really hard to explain in without having the emission tied to the rotation of an object. It's well fit by the rotating vector model, which is what we fit for pulsar polarization angle swings. And so it really looks like you have an object, like a lighthouse beam swinging across your line of sight. And so the interpretation here is that this polarization angle behavior is because the emission is tied to the rotation of the object, i.e. is coming from within the magnetosphere of the object. And so this polarization angle swing is very naturally explained in the magnetospheric models tied to the rotation, similar to pulsars. And it's really hard, I think, to explain in the non-magnetospheric models because you don't expect it to change, the polarization angle to change so smoothly over such a short time. Okay, and I mentioned earlier that FRBs are highly polarized. This is a plot here showing the polarization results from the DSA sample of FRBs. And here it nicely shows that most of their sample is very highly linearly polarized with little to no circular polarization. And this is quite a common observed property of FRBs is high linear, low circular. However, sometimes, rarely, we see high circular polarization from FRBs. And in the literature, it's been reported up to 90% circularly polarized emission. For magnetospheric models, you can get 100% linear if you're looking at the emission kind of down the barrel of the gun. And then you can introduce a circular polarization if you let your beam move a little bit off axis. And the same is true for the non-magnetospheric models. However, it comes with a catch. In the non-magnetospheric models, as soon as you move off axis, you expect the flux to drop very quickly, to the point that the predictions are that we shouldn't be able to detect off-axis emission in these non-magnetospheric models at cosmological distances. So that really challenges this interpretation. I will add, though, similar to the temporal variability, you can have propagation effects in the surrounding circumburst environment that introduce significant circular polarization, such as Faraday conversion. The one question that remains in my head about that interpretation is that a lot of these studies that have circular polarization, these have been done on repeating FRBs. And in these studies, they actually see changes of the polarization burst to burst on short timescales. It can go from very high linear to very high circular in maybe minutes, kind of burst to burst variability. And so in my mind, the question then is, do you expect the line of sight plasma conditions to change that rapidly in these environments? Maybe, but I think that remains to be explored, whether that's really a viable conclusion for significant circular. Okay, so finally, I want to talk about using scintillation as a probe of the emission physics. So I'm going to start with an analogy. Imagine that we're all outside looking up at the night sky. Well, it's night here. I know it's morning there, but later on, looking up in the night sky, then we'll see stars and we see planets. The stars are twinkling because they're scintillating and they're being scintillated by Earth's atmosphere. But the planets are not. And the reason is because the stars, they are so far away that they appear point-like with respect to the diffractive scale of Earth's atmosphere. And so the coherence is met and we get scintillation. But planets, they're much closer, and so they appear larger on the sky, and we lose that coherence that's necessary for scintillation. So this idea that scintillation is tied to the apparent size of these objects, that same concept can be applied to FRBs. So here is a really nice figure from a paper that was led by Pawan Kumar and Paz Benyamini and collaborators. And this outlines exactly what I've just said, but for FRB emission models. So the analogy to stars, the magnetospheric models are predicted to have very small emission sizes. And so they should be point-like with respect to the diffractive scale of a local plasma screen. And in that case, then we would expect to see scintillation like we do in stars. By C scintillation for FRBs, what we're talking about here is flux modulation as a function of frequency. You see these peaks and troughs very strong. That's what we see as scintillation. For non-magnetospheric models, though, the emission region is much larger. And so this is more like the planet's case, where we're not going to have the coherence necessary for this strong modulation of scintillation. And then the prediction there is that we should get weak modulation, so kind of smaller peaks and troughs, or not see scintillation at all is a reasonable outcome. And we know we can see scintillation in FRBs. There's many examples in the literature. By C, I'm talking about this flux modulation as a function of frequency. Basically, these stripes that you can see in the dynamic spectrum, that's scintillation. And so we characterize the scintillation using the characteristic size of these stripes, as well as the strength of the modulation, the intensity as a function of frequency. And we measure this in an autocorrelation function. So we take the burst spectrum, correlate it with itself, and then we fit a Lorentzian to that. The width of the Lorentzian tells us this characteristic size, characteristic width of the scintils, and the height of this Lorentzian tells us the modulation or the strength of the scintillation. And from these measurements in the literature, all of these studies have come to the conclusion that the scintillation that's been seen before is coming from the Milky Way's, likely coming from the Milky Way's interstellar medium. And that's just too far away from the FRB to have any kind of powerful constraint on the emission size. You really need the screen or the lens in this case to be much closer to the FRB to have the distinguishing power between these models. And so that's where this asterisk comes from, that the scintillation really has to be coming from the host galaxy. Okay, so that leads me to bring back this guy that we saw earlier. I mentioned earlier this FRB was interesting because it had this smooth S-shaped polarization angle swing, and that allowed us to conclude that it's tied to the rotation of the object, likely coming from the magnetosphere, and therefore probably from a very small emission region size. And so for this FRB, we took its burst spectrum, we computed its autocorrelation function, which is shown in orange. And immediately two very clear scales of scintillation show up in purple and in blue. And so the same logic that we applied to where the planets, like the apparent size of planets is large, and so you lose this coherence that's necessary for scintillation, that also applies to these screens, i.e., if these screens are too close together, the screen 2 looks too big from the perspective of screen 1, and you lose that coherence. And so what you need to do is you need to place them far enough away from each other that this screen, if you can see me, the screen 2 has to be point-like with respect to screen 1 in order to explain why we've seen these scintillation scales. And so that allows us, if you do the maths, which I won't go into here, but feel free to read the paper, that lets us say that one of the screens is in the Milky Way's interstellar medium, and the other is in the host galaxy of the FRB. So we've found scintillation from the host galaxy for the first time in NAFRB, and that allows us now to explore what the emission region size is. The last problem that we have is that there's a degeneracy between where the screen is and the size of the screen. So you can imagine if you bring the screen really close, then the emission region size has to be really tiny in order to keep it a point source with respect to the screen, or you can move it further away and let the size be a little bit larger. And that degeneracy is plotted here in green. But the good thing is that we know that the screen has to be within the host galaxy. And so that lets us put this blue line here and allows us to place an upper limit on the emission size, very conservatively, of 3 × 10⁴ kilometers. And for comparison, I'm plotting in orange. The shaded region is the allowable sizes for the non-magnetospheric models, and the magnetospheric models are in the shaded purple region. And from this upper limit, you can see that we're below the lower bound that's allowed for the non-magnetospheric models and broadly consistent with what's allowed for the magnetospheric models. And so this detection of scintillation has an emission region size, allowed us to constrain it to a magnetospheric process, and tells us that it's not a non-magnetospheric process in this FRB. So as you can see, now that I've completed the table, we have growing support for magnetospheric models here. The major caveat that I want to scream and shout is that these, I think everything I've talked about here are all single source studies or very small samples. So it's unclear whether this is reflective of the broader population or whether we're really kind of focusing on the weird ones that we can do this really detailed analysis on. And so it's really important that we can scale all this effort up to really explore what's happening on a population level. But for now, this is what the data is telling us. And I want to also say that I don't actually think that it necessarily think that it's all just a single model and that explains everything. I think that in the literature, there's already evidence for multiple emission processes happening from even a single source. So here are some bursts from repeating FRBs in the literature that look very interesting morphologically. They have sharp structures on top of broad drifty structures. They have structures that look like maybe they're changing drifting or changing DM. And in this Hewitt et al. 2023 paper, they draw the analogy to solar flares, where the sharp components are thought to come from magnetic reconnection near the solar surface, and the broad drifty components are thought to come from shocks propagating out in the solar corona. So completely analogous to our magnetospheric and non-magnetospheric cases. Although solar flares are totally different, like energies, frequencies, timescales, basically completely different. But the morphology is strikingly similar, at least to draw the analogy. And then there's also growing evidence for a break in the energy distribution for repeating FRBs. And so that gets me excited. Maybe these low energy bursts have different emission physics from high energy bursts, and we can use techniques like scintillation to potentially answer that question and disentangle the emission physics even under a single repeating source. Okay, so I'm just about out of time, so I'll leave you with my summary. I think that there's definitely a huge diversity in the FRB properties that we see, and I think this is likely a mix of effects from potentially different progenitors, different emission processes, and different complex plasma conditions in the vicinity of these extreme objects. In the case of progenitors, we're tackling that by localizing FRBs to their local environments, which we heard about earlier in the week. I'll just highlight this recent result from the Chime Outriggers project, where we localized a non-repeater to 10 parsec scale in its local environment. But we also heard just from Vic about how multi-wavelength counterparts could really tell us exactly what the progenitors are. So there's a lot of headway being made there. For the immediate environments, the FRBs hold so much information about the complex plasmas local to the source. And I wanted to highlight this really cool result that I think is really cool. Where this FAST were monitoring a repeating FRB, they find that the rotation measure is pretty constant with time over a very long time scale, and then out of nowhere it jumps up by an order of magnitude before decaying back down very quickly to the kind of baseline level. And the interpretation there is that you have the FRB source in a binary system with a stellar companion, and that stellar companion produces a magnetized flare that we see here in the RM, which is kind of cool. And then I've talked about the emission physics, and I think there's growing support for the magnetospheric models. And if you take one thing away from my talk, I think scintillation is going to be an incredibly powerful tool for understanding the emission physics of FRBs broadly. Thank you, and I'll take any questions.
Thank you, Kenzie, for this excellent talk. Questions?
Hey, Kenzie, great talk. I was just wondering, where does hyperactivity come into this? Basically, could you say that if you have a hyperactive repeater, it is going to deposit a lot of energy into the surrounding medium, and therefore, at certain point, you should just not see a non-magnetospheric emission because there's just no medium left?
What do you mean by no medium left?
So I'm just wondering if the energy that is deposited into the medium is enough to just push it away, and therefore you couldn't have shock models.
Oh, I see what you mean. I think so. My gut feeling is that I don't think we understand the plasmas well enough. So, for example, the scintillation result, or I guess the big debate in the field is whether or not the plasma in the magnetosphere of like a magnetar would even let the FRB escape. And so the fact that we've shown with the scintillation result that the FRB is escaping from the magnetar means we kind of either don't understand the plasma properties, or the magnetar is flaring, creating like a cavity that we see the radio emission through. So at least on that front, I think we just don't understand enough to say that for sure. But yeah, it's an interesting idea if you could use the amount of energy that's released to get rid of the circumsource plasma that you need for the shock model. But then you're inherently assuming that it's magnetospheric in that case.
Right. Yeah. Thank you.
I'll also add that there was a paper a couple months ago, also led by Pawan, where they indicate that perhaps the repeaters, like the hyperactivity, is just a reflection of distance. And so we're only seeing the hyperactive ones because they're more nearby, potentially. And so it's possible that all FRBs are kind of equally hyperactive.
Hi, Kenzie, this is Baz. Thanks for the talk. Maybe I can just comment on the last thing because it's our paper with Pawan. The idea there is not that all bursts are equally active, all sources are equally active. Indeed, we find evidence that sources have very different activity rates spanning many orders of magnitude. This is apparent activity rates, which could be due to geometrical effect, selection that is kind of embedded in through that. But once you fold that in with detectability, you do end up getting that highly active repeaters will be observed slightly closer than non-repeaters or less active repeaters. So that's just a comment. But regarding the very nice scintillation work, first of all, I agree with you that this is one of the best ways that we have to constrain the different models. And I was wondering how many more bursts are out there for which this kind of analysis is feasible. What are the sort of expectations, for the year or two to come in terms of, are we going to get many more of these? Can we expand it to bursts with very different properties to really see how generic it is?
Yeah, that's a good question. So Chime has thousands of FRBs already. And I think about maybe like 2,000-ish have baseband data. So we need baseband data as the first thing. So we have a couple thousand with baseband data. However, I think we also, at least in most cases, would need to know the redshift. And the reason is because we need to, there's that degeneracy between where the screen is and the source emission size, and to get stronger constraints on where those screens are with respect to each other, you need to know the redshift also. And so I think we would be limited even further into the ones that also have redshifts. And so the sample of those is smaller, but it is growing with the outriggers. Yeah, so I think that it's more worthwhile that we focus on these scintillation studies on the ones that also have redshifts.
Yeah, okay, thanks.
So just on your very first slide, and I'm sure this must have been discussed earlier in the conference. I just arrived yesterday. So when you talked about observations of FRBs, right? Are there results or limits at microwave frequencies from Planck, SPT, or ACT? I think last month ACT collaboration had a paper on, I think, limits from the crab pulsar. So are there results or limits from FRBs? Or
So
from ALMA?
You're just referring to like multi-wavelength counterparts?
No, microwave frequencies. Planck,
Microwave.
ACT, SPT.
Not that I know of. I guess Vic would be the person to ask, having just talked about counterparts. But I can remember maybe one study with ALMA, but I don't think it's, if you're talking about looking for prompt emission, I don't think so.
Okay. But from these models, they don't predict anything at microwave frequencies, right?
Not that I know of. Primarily, these models predict the higher energy kind of X-ray emission.
Yeah, I have one question. Yeah, hi. I had a question regarding the break that you showed. So can you say about something about like what kind of two different emission mechanisms could be in respect to close-in, like the magnetospheric model?
So I actually think, well, I think it is possible that it could be one is a magnetospheric model, so perhaps the low energy burst of the magnetospheric model and the high energy burst are the shock model from a single source. I wasn't necessarily implying that they were both magnetospheric with different flavors, but that's also, of course, possible. That would be a bit harder to show, I think, just because the scintillation results that I mentioned is really probing the size, and so if it's both magnetospheric models, I think you could probably expect them to have comparable emission sizes, at least from theoretical predictions, whereas it would be easier to show that the emission sizes of the pink bursts are smaller than those of the yellow bursts, for example, here.
Yeah, one thing could be, could the high energy burst be explained by propagation effect like plasma lensing?
Maybe. I would need to think about that. I think so. Plasma lensing would introduce more spectral structure. So that's one thing you could look at, is if you compare the frequency structure of these high energy bursts with the low energy bursts. That becomes a bit tricky just because when you're in the kind of lower energy regime or lower flux regime, the spectral and temporal structure can kind of all mesh together because you're in kind of low signal to noise. So I think that would be kind of hard to do meaningfully, but it's worth looking at, I think.
Yeah, thanks.
Yeah, thank you. Just we'll take one question from online. Ramesh.
Hi, can you hear me?
Yeah.
Hi, Kenzie. That's a very nice overview. I was enjoying it from start to finish. Yeah, that's you make a very good case, and you sort of put together everything to argue that observations are leaning more and more towards magnetospheric models. Sometimes, at least my vantage point of view, I get a feeling that probably progenitors might be better understood or better converged, by understanding the emission processes, which is what you are essentially trying to bring across. I have thought among all the things that you have listed, perhaps that temporal structure and variability is the most constraining one. And the kind of scales and time scales that you are talking about is essentially similar to what has been discussed or an pulsar microstructure and giant pulses and that. But you also mentioned that that is not quite entirely unique in the sense that there are ideas out there that explains a similar sort of things, hopefully at least qualitatively from other things. And could you slightly elaborate on that? Are they that constraining us, the kind of ideas that are floating around for, say, understanding pulsar microstructure?
Yeah, maybe I can jump back to that slide quickly. Yeah, so for the microstructure, the pushback that I've had from the non-magnetospheric theorists, the two things. One is that you can introduce kind of clumpiness in the surrounding medium so that the shock is hitting into this clumpy media, which then you're lighting up these small clumps and you get smaller timescales. That's fine, but it's not as compelling as saying, oh well, the magnetospheric models just explain it. However, there's these studies which are exploring these nonlinear propagation effects. So you need this electron-proton plasma in the surrounding environment, which maybe. And then if your radio waves propagate through that, then the emission gets split up into pancakes. And in these predictions, you can, it depends, I think, on the properties of the plasma, where it is relative to the FRB, et cetera, but under certain conditions, you can get down to kind of microsecond, sub-microsecond scale variability just through propagation effects. But these studies are kind of in their infancy. And so I think a lot more effort probably has to go into understanding this to really know for sure. But yeah, I would say I think there's these timescales can be naturally explained in the magnetospheric models. You have to tweak and add bells and whistles to the non-magnetospheric models in order to explain it. So it's not impossible. Whereas for the scintillation, for example, the strength there is you can't introduce a propagation effect to get the small emission size. So there isn't really, as far as I know, a caveat to the size constraints that we have. And so that's why I personally think that it's a stronger metric. I've not heard as much pushback.
Okay.
Can I quickly
comment?
Right,
no, that's very useful. Very quick question. So the example that you showed, was it the highest resolution structure? Was it for a repeating FRB or non-repeating one?
Yeah, this example is a weird one. It's a repeater, but it's also the repeater that lives in the globular cluster in the M81 galactic system. So it's weird for a few reasons. But we have seen kind of microstructure in the case of the first repeater and also the third repeater, which are in different environments. So drastically, I'll say drastically different environments. So I don't think it's a propagation effect for that reason.
Thanks.
Thank you.
Okay, if I can, I wanted to quickly say something about the temporal variability in blast wave models. So, like Kenzie said, it's possible if you have a clumpy environment to have some variability. However, this comes at a great loss in terms of efficiency. which is already very low for these models, and probably with these additional losses, it's already unfeasible. The other way is this self-modulation instability, this pancake formation that Kenzie just mentioned. This also is limited in what it can do. You can't get to the 60 nanosecond scale that was seen in M81. And in addition, you expect a very specific structure in terms of the pulses and the gaps between pulses. Once we start really studying the shape of the light curve, we can potentially look for this or rule it out. There's a specific relation that one expects in this case between the variability scale and the luminosity and how it scales with the frequency. So that is one thing that can be checked, and multiple scales, if you have a long gap and then a very rapidly rising spike that declines more slowly, this will be very difficult to do with this self-modulation instability, where all of these things are related to the same scale, which is basically the this scale of the wavelength of the instability that develops. So it's an interesting idea, but it has very specific predictions that can be tested.
Yeah, thanks, Paz. I don't think I'd appreciated that the light curve shape has information. I will just add, like, from an observational perspective, in the case here, when you're at these kind of short timescales, you have effects like amplitude modulated noise, which introduces structure here that can't be interpreted as the isolated shots. And so characterizing the light curve, at least on these timescales, would be quite difficult, I would say. But we should think about it more. Thank you.
Yeah, thank you, Kenzie, and for initiating this very interesting discussion, and especially joining at a late night. Thank you. Thanks.
Thanks.